Okay, so let's get started. Okay, so last week we talked about some specific machine learning method. I think we talked about the decision tree. Okay, so a quick review. So we talk about decision tree. Okay, so in the decision tree, we're talking about entropy. Okay, and then we talk about KNN. So in KNN, so through KNN, I think we talk about the some concept like inductive bias and some proof. Okay. So then we talk about the cross validation. So it basically is part of the model selection. Okay, so that's actually a very important part of machine learning. Okay, and for the cross validation and model selection, so we talk about the parameters, hyperparameters. Okay, so what are their differences? Okay, so the hyperparameter gives you the hypothesis set. Okay, so basically you define a hyperparameter means that you define a hypothesis set, and then you train the model given the hyperparameter means that you select the optimal function from the hypothesis set. Okay, so that's basically the when we talk about machine learning training, so we are talking about selecting a optimal function from the hypothesis set. Okay. So let's keep talking more about the methodology. So during the methodology, I'll also give you some key concept during for the machine learning. Okay, so so remember that because of the time limits, there are some methodology I cannot cover. So one of the most very important one is the support vector machine. Have you heard about this? Support vector machine, SVM, or there's another version called support vector regressor, SVR. This is SVM. SVM is for classification, SVR is for regression. So these two are very similar. Okay, so basically, I do not have time to cover this. I think one reason is that this is no longer popular. But if you want to find a job in the IT company, many of them they will interview on SVM because SVM is closely related to the optimization and duality. Okay, so the derivation of the support vector machine is based on the concept of optimization and duality. Okay, so if you're interested, I would suggest that you to read a little bit on what is support vector machine. But this one not very used recently. Okay, I'm not sure what's the reason. Okay, the performance is okay, but yeah, it's not popular anymore. Okay, so usually when we talk about SVM, okay, so there is a very important concept that will be so basically, after introducing the SVM, there will be a very important concept called kernelized SVM. And there is a very important technique called kernel trick. Okay, sorry, kernel trick. Okay. So basically, the kernel trick can transform many linear. I would say like that. Kernel trick can transform many simple machine learning method to have better capacity. Okay, So this is actually pretty popular and famous long, I think 10 years ago, but maybe you never heard about this recent years because no one is using this. Okay, but the mathematics underlying this kernel trick, this basically there's a group of method that is kernel method. Okay, so I highly suggest that you try to read it. Maybe it's not useful, but for sake of enhancing your mathematical background, this is pretty good. The whole formulation is very elegant. Okay, so basically, it just says that after you do some transformation and you just replace a operator, and then your model becomes much more nonlinear and much more powerful. Okay, so that's actually from SVM. So once you have SVM, and you can simply change a module, so become a kernelized SVM. Because SVM is linear decision boundary. Okay. Linear decision boundary is not good because we want to have more complicated decision boundary. Okay, so the kernelized SVM can have like very complicated decision boundary. So I think this is the SVM and the kernel trick is if we are taking a very classic machine learning subject, this will definitely appear because this is a very important concept, because it's not from practical perspective and because of the time limit. So I skip this part. Okay. So if you're interested, I highly suggest that you at least understand what it is. Okay. So many interview question is actually from here. Okay, so there's another part I'll skip, which is linear regression and logistic regression. I think Professor Zhang talked a lot, especially for the linear regression. I'm not sure whether he talked about the logistic regression or not. Yes. So you know what is linear regression, you know what is logistic regression, okay? So from a machine learning perspective, a very interesting thing is that logistic regression is for classification. Okay, so the name is regression, but from a machine learning definition, this is for classification because logistic regression is actually for binary classification. Okay, so basically, I think Professor Zhang talking linear regression and logistic regression from a statistical perspective, but these two models are also well-known machine learning model. So maybe I just have a quick question to invite you to consider. Linear regression is okay, right? So for logistic regression, it can do binary classification. What if I want to do multiple class classification? How can I use logistic regression to do the multi-class classification? Okay, so that's actually a very interesting question. So it's possible. Okay, so there are two approaches. So one approach is that you train, for example, you have K class. You train K logistic regression, and each of the regression just separates K or not K. Okay, so this is a binary classification. You just train K or not K, 1 or not 1, 2 or not 2, 3 or not 2, 3 and not 3. Okay, then you use some voting approach to get the final results. Okay, I think this is actually a famous approach. There's others I kind of forgot. So there's another method, so that you can also do the multi-class classification. I kind of forget. Yeah, maybe I put it later. Okay, so basically, the idea is that you use multiple classification and then you just combine the results. Okay. So what Professor Zhang have not talking about, I think I just give you a quick review of linear regression. Okay, so did Professor Zhang talking about the vector form of linear regression? No. Okay, so then I talk about this part. Okay, so essentially, the linear regression can be written as a y equals beta x. Beta is a vector and x is a vector. Okay, so so this is you can consider the intercept or non-intercept. Okay, so the intercept in machine learning, usually we call it bias. We don't use the intercept, we use bias. Okay, so we call it coefficient and bias. So remember, how do we organize the data? Our data is some X matrix. So basically you have number of data, I equals 1, I equals 2, all the way to I equals n. And then you have D equals 1 all the way to D equals D. Okay, so this is a n by D matrix. Okay, so what is your coefficient? So basically you need to have a beta or W. So depending on notation. Okay, say for example, we have a beta. So what is the dimension of the beta? Beta should be dimension D, right? So what if you want to add the bias? So usually what we are going to do is that we can add one column here and we put all 1. And then we add one more vector, which is alpha. So that gives you D plus 1 as the coefficient. Okay, so no matter it's called bias, intercept, coefficient, in the linear regression, in the machine learning narrative, we call this parameters. Okay, so beta is your parameters. Okay. Then very straightforward, you have beta times x. So this is so you can write 2 versions. So I think I just write x times beta, right? So in my case, x times beta. So basically this is n by d. This is d by 1. So this gives you n by 1, which is y. Okay, y is a n by 1 matrix. Okay, so basically what we are going to do is that we want to find the beta such that the y is close to x times beta, right? And you can define a distance between y and x beta. So basically you can define multiple distance. Okay, for example, you can define the 2 norm. Did I talk the different norm? Do you know this? Yes, 1 norm, 2 norm. Do you know the definition? Maybe I just say one more words. Okay, so essentially we have a notation. I'm not sure you know this or not. This one. Okay, have you heard about this? This we call it P norm. So norm in Chinese is called mo. Okay, so basically you think of it as some length. Okay, so we want to find calculate the length of beta. Okay, beta is a vector. Okay, so P norm is defined as, so each element of beta, so for example, beta 1 power of P plus beta 2 power of P all the way to beta B power of P. And then we take the root of P. Okay, so this is the definition of P norm. So this looks weird, right? But if you look at 2 norm, this is basically beta 1 square plus beta 2 square plus all the way beta d square and the square root. Okay, so this is a Euclidean distance. I think I talked about the Euclidean distance last week, right? So, and also if it's a beta 1, this is basically Manhattan distance. Okay, so the P norm is used to measure the length of your vector. Okay, so basically we will have beta P norm equals 1. This if and only if beta is a 0 vector. Okay, so this I think is clear. Okay, so basically beta, the norm measures the length of the beta. So here you can see that we basically want to minimize y minus x beta, right? So you can actually choose some norm here. Okay, you can choose a p norm here. And if you choose a two norm, then we call this a least square. Okay, least square basically is that you want to minimize the square, right? So basically it's talking about the minimizing the two norm. Okay, so you can also minimize the one norm. It's okay. So it's not a standard linear regression, but it's still a linear model. Okay, you can also do 3 norm, 4 norm. It's okay. Okay, so it's valid. Okay, so there are several very tricky norm. Maybe I just because we talk about this, you should know. Okay, so there's two very tricky one. One is zero norm. Okay, another one is infinite norm. Okay, so the infinite norm is actually very simple to imagine. It's basically you take the limit of p to goes to the infinite, and then you look at the p norm. So what's this? The p norm, you take p to the infinite, positive, of course, positive infinite. Okay, so if you look at this original formulation, if your p is super large, what will happen? So this is your calculus study. You can, I think you can definitely show that the largest one will dominate. Okay, for example, this is 1, this is 2, and this is 3, and then 3 to the power of p, this one will dominate. Okay, because this one will dominate, then eventually this gives you maxima of beta. So it's max element in beta. So maybe I write it like beta d, max d. Okay, so it's basically taking the largest element from the beta. So this is called infinite norm. Okay, so what is zero norm? Zero norm is by definition. Okay, so this is the number of non-zero in beta. Okay, the number of non-zeros in beta. So it's counting. Okay, so beta zero norm is basically a counting of non-zero. Okay. So so basically this gives you all the p norm. Okay, norm from 0 to all the way to the infinite. You have this full picture of a p norm. Okay, in different cases you may use different norm. Okay, maybe later you read the paper, you'll find this notation. Okay, then you will know what's this. Okay, and here my definition is for vectors. Okay, so for matrix, there's more norm. Okay, for example, there's a norm called nuclear norm. Okay, and there are a lot of other norm that is particularly used for matrix. Okay, so all the vector norm can be used in matrix. Okay, p norm is still defined. P norm is still valid. Okay, you still have p norm for matrix, and there are other norm that is particularly defined for matrix. The most commonly used one is this one, not nuclear norm. This one is particularly important in many. You definitely will read this in some machine learning paper if you are doing some related study. Okay, so if you're interested, just try to read this. Okay. So having this, you can see here, we are defining a. So basically, the linear regression can be defined as something like this. So basically, you are looking at two norm, okay, and two norm, which is difficult to do the derivation, right? So usually we will take the square, then it becomes two norm, square of the two norm. Okay, so please make sure that you understand the meaning of this two and the meaning of this two is different. Okay, So every writing has a meaning. So this is rigorous mathematics. So if you're writing something, you please make sure that you know what's the meaning. So here we put the square here because we want to take the derivative easy. We want to take the derivative easily. Okay. So this is actually a vector minus vector. So it's still a vector, right? So then another question. So given a vector, what's this? Do we have a simple, this is basically the v1 square plus v2 square all the way to vd square, right? So you just ignore this square root, right? You take the square, then you don't have this one, right? You just have the sum of the square, right? So what's this? This is v transpose times v. Yes. So the square of 2 norm is actually the transpose of this vector times this vector. Okay, so this you can prove, right? So the 2 norm of v, square of the 2 norm equals v transform times v. Okay, good. Yes. Okay, so then let's do some math. Okay, so y minus x beta, this is a vector, right? Then this equals to y minus x beta transpose times y minus x beta. Okay, and so how do you do transpose? It's basically beta transpose x transpose y minus y transpose minus beta transpose x transpose, right? Times y times x beta. Okay, so we expand. So y transpose times y minus 1 transpose x beta minus beta transpose x transpose y plus beta transpose x beta. Yes. Yes. So have you learned the matrix calculation? I think so. Yeah, in your linear algebra in your undergrad, you should learn this. Okay. So one observation is that these four are scalar. Okay, so these all four numbers are scalar. Okay, even though this looks scary, but it's scalar. Okay, if it's scalar, then the transpose of a scalar is the scalar itself. Okay, so it's scalar, right? Then this is scalar. Then this equals the transpose of it. So this equals y transpose x and beta. Okay, because for the scalar, 1, the transpose of 1 is still 1. Okay, so then this, you can see this 2 is the same. Then you can do y minus 2y transpose x beta plus x beta transpose x, something like this. Okay. So so basically this is our objective, right? So basically we want to minimize this. Okay, we want to minimize this means that what we can change, we can change beta, right? So so basically what we can do is that we can set partial L partial beta to be 0, right? Which we find the minimal location. Okay. So how do we calculate this one? So partial L partial beta, this gives you 0 because this is not related to beta, right? So maybe have you learned matrix calculus? So AX, partial x, what's this? This gives you A transpose. Okay, so matrix calculus. Okay, so here you can see that this gives you X times Y. 2x times y, negative 2x times y. Okay, sorry, x transpose y. Okay, plus this one maybe later you can search. So this gives you x transpose x. This equals 0. Okay, so then we make it, this is E0. Also, we have x transpose x equals to x transpose y. Sorry, where is my beta? Sorry, beta is here. Okay, then what you have is beta equals x transpose x, x transpose y. Okay, so this is your solution for beta. Okay, so have you learned this from Professor Zhang? But you know that there's a closed form for linear regression, right? So that's how you derive the closed form of linear regression using the matrix calculus. Okay, good. So here you can see that we assume that x transpose x is invertible, which may not be true. Okay. So what is the dimension of x transpose x? I think my direct derivation is kind of correct. I'm not sure, but later you can check. Okay, so x transpose x, the dimension should be d by n times n by d, right? So it should be d by d, right? So you can imagine that if and do you know the rank of x transpose x is definitely smaller than the minimum of n by n and d. You know this? This is from your linear algebra. Okay, so you can see here, if n smaller than d, x transpose x is not invertible. Okay, that creates a lot of issue. Okay, that in that case, you don't have a unique and closed form for beta. Okay, what does it mean by n smaller than d? Means that your feature is more than the data. Okay, so think of the DNA, the example I mentioned a long time ago. So basically, you want to look at which DNA is affecting people's some appearance. So essentially, you have a lot of DNA pieces, but the number of people that you have, the data, is actually limited. So the number of the population in the world is actually smaller than the number of genes, right? So in that case, you have this issue. Okay. So in many cases, you have this issue. Okay. So if you imagine there's an image or there's some high dimensional data, you also have this issue. Okay. So if this happens, we call this a underdetermination. So this is from linear system. In Chinese, it's called 限定. Okay. Then what you can do, basically there are multiple solutions. There are two famous ones. One is called lasso, another one is called ridge regression. Okay, so maybe I skip the detail, but the idea is very simple. So previously you do this one, because here you find that the beta is, if this one is not invertible, then you have infinite solution of beta, right? So over those beta, which one I think is correct? I believe that the beta should be simpler. Then I add this one. Okay, I add a term. What does this term mean? This term means that I want the data as small as possible. So I add a norm of beta. So over all those beta, I trust the beta that is smallest. So why? So this is from our principle, right? Occam's razor. The simplest is the best. Okay, so this gives you lasso, and or you don't want to use the P1 norm, you want to use the 2 norm. This gives you the ridge. Okay. This gives you the ridge. These are the lasso regression and ridge regression. Okay, so those two are very useful when your data dimension is very high and even higher than the number of data. Okay, so that's why these are very useful for the bioinformatics. Okay, so this is another perspective of linear regression. This is a view from machine learning perspective. You can see that I don't care about all those hypothesis testing. I don't care about all those statistical meaning. So here is a pure derivation. So then we there's an issue, then you add something. Okay, so those stuff has a name. So these things has a name. Okay, we call it regularization term. Okay. So remember last week I mentioned that given a machine learning method, you must have some parameter that can make your model overfitting or underfitting. So you should have a parameter that can tune the model, right? So that's some basic concept of machine learning. So linear regression actually does not have such a parameter, right? So then people don't think the linear regression is a very suitable machine learning approach. It's more like a statistical approach. But lasso and the ridge does has this parameter. So it's actually here. It's called lambda. Lambda is here. Okay, we put a weight in front of the regularization term. So what happens if lambda is small? It's overfitting or underfitting. This will gives you underfitting. Sorry, overfitting. Okay. Then if lambda is almost infinite, this will gives you the underfitting. I think it's easy to understand, right? Lambda gives to almost infinite means that you just believe that beta is 0. This is a super strong inductive bias, right? So here you can see that you are using lambda to trade off between the data that you learned and also the inductive bias that you impose. Okay. Okay. So lasso, when we talk about a linear model in machine learning, usually we are talking about lasso and ridge. Okay. The original classic linear regression is not a very suitable machine learning approach because there's no hyperparameter to tune. Okay, this has a hyperparameter lambda to tune. Okay, so if you are interested in lasso and ridge regression, there's I highly suggest that you read online. There is quite a lot of discussion. Okay, so in general, there are some observation which is actually difficult to prove. Observe is that lasso gives you a sparse beta. What does sparse beta mean? Means that there's a lot of 0 in the beta. Okay, and ridge gives you a dense beta, but with a lot of small values. Okay. So you may ask why. It's tricky. Okay. There's a lot of explanation. If you're interested, please check online. But this one you should remember. Okay, lasso has a very good feature that it gives you a sparse beta. Why the sparse beta is useful? It means that there's a lot of 0. Okay, 0 means that this variable is nothing related to y. Okay, so this is a automatic feature selection. Okay, so Lasso automatically select feature during the training. Okay, so this is a very good feature, particularly in bioinformatics, because you can automatically discard a lot of gene pieces. Okay, you can focus on some specific items. Okay, but the reach does not give you this property. Okay, reach still gives you a beta that all of the element has numbers, but many numbers are very small. Okay, so if you want to know why this relates to a lot of issues, I'll skip the explanation. Okay. So basically, people are developing mathematic proofs on this for a long time. Okay. Okay, so I just gave a quick overview. I think this is just a quick summary of the machine learning perspective of linear regression. Okay, so so I think it might be a little bit different from the statistical perspective. The statistical perspective care about the hypothesis testing, care about the random error, all those things. Okay, so machine learning does not care about those. They just make sure it's not overfitting, not underfitting. Okay. Okay, so then let's talk about another method. So this method is actually pretty straightforward. I'll quickly go through it. Not too many mathematics underlying the perceptron, but this one is pretty important because this is actually the foundation of deep learning. Okay, so we call it perceptron. Maybe you haven't heard about this because this method, no one will going to use it in practice. Okay, so this methodology is developed back in 1960 something. Okay, it's a super old methodology, but this is actually the foundation or cornerstone for the neural network, so which is called perceptron, 感知机. Okay, so the idea of a perceptron actually comes from the psychological brain science. Okay, so basically we want to use a model to simulate how your brain, how the neurons in your brain works. Okay, so the perceptron looks like this. Okay, so essentially you think of a input. Okay, x. So x has d dimension, for example. So for each of the dimension, you input to a unit like this. So basically you are doing two step. Okay, so essentially you have a connection. Okay, on this connection you have a weight w. Okay, what we are going to do, very simple, w1 times x1 plus w2 times x2 plus w3 times x3. Okay, so you calculate this, and then you do the summarization, and then you apply a step function. The step function, here we are using a very simple one. So basically the step function says that if it's greater than 1, we say the output is 1 if it's greater than 0. It's 0 if smaller than equal to 0. That's it. So it's just a if else. Positive, output 1. Negative and 0, output 0. Okay, so this whole structure actually simulates a neuron in your brain. So essentially you can see here, your neuron is something like this and it's connected to other neurons. And then you receive the signal from other neurons. And because the connection of different signal is different, so here we are using weight to represent the strength of connection. Okay, so you have the signal, you have the signal, and then you have the strength. You use the strength multiplied by the signal, and you sum them together. So this is a total signal that you received. And if the signal exists some threshold, means that your brain, your neuron is activated, then we say it's 1. If it's below some threshold, then we say it's not activated, then we say it's 0. So this gives you a simple neuron model. We call this a perceptron. Okay, and I think from this definition, you also notice what's this used for. Okay, so this is used for binary classification. The 0, 1 is actually used for binary classification. And I think you might also notice that this is very similar to logistic regression. Okay. If this one, I change it to logit function. Okay, this becomes logistic regression. Okay. If I use logit function as a step function, then it becomes logistic regression. Then this is no longer perceptron. This is logistic regression. Okay, so you can see that they are quite similar. The perceptron is actually way older. Okay, so this is developed almost half century ago, more than half century ago. Okay, 70 years ago. Okay, so this is a very simple and basic approach, but I want to mention this because this one is very useful, very important concept for the neural network. Okay, so then one thing I want to mention, talk about is the learning procedure. So this is actually very typical and give you a flavor of how the machine will learn. Okay, so the machine, the perceptron learning is actually very simple idea. It's basically like this. So your output is either 1 or 0, right? So you for example, here you have some output, and then you have some target. Okay, we find that the arrow equals the target minus your output. So there's an arrow. So if your arrow is larger, if your arrow is positive, then basically means that we want to increase the output. If your arrow is negative, then we want to decrease the output. Very straightforward idea, right? How can we achieve this? So the people that think of a very smart idea, that what you can do is that you can either add or minus a x to the w. Okay, so let me do some proof. Okay, so here I say that w is a weight, the old w. Okay, so what I can do is that I can calculate the new w, which is w plus. W plus, let's say we define it as w plus x. Okay, I just add this data to the w. They are the same dimension, right? W is d dimension, x is d dimension, so they can add. So why I'm doing this? Because I want to look at this feature. So w x transpose w. So basically we are calculating this number, right? X transpose w. So x transpose w plus equals x transpose w plus x. This gives you w transpose x transpose w plus x transpose x. This is x transpose w plus x 2 norm, square of 2 norm. Okay, so this one is greater and equal to 0, right? Because it's norm. Then this whole thing is greater than x transpose w. You can see that by adding x to w, the output becomes larger. Okay, by adding the x to w, the new x times w becomes larger than the previous x times w. Okay, so vice versa, if you minus a x, then the output will be smaller than the previous one. Okay, so this is actually a very smart idea that you just use data to update your parameter. Okay, then here gives you the final updating procedure. It basically says that we call this a error correcting method. Essentially, very straightforward. If your perceptron predicts 0, but the answer is 1, then you add the data to the weight. If the perceptron is 1, but you predict 0, means that you are larger, then you minus, you subtract the data to the vector. Okay, let me show you an example. So here, let's say we are running an algorithm for a 3-dimensional data. So this is n by 3, 4 by 3 data. Okay, so the output is 0, 1, 1, 1, and here is your input. Okay, so we use the activation function. It's basically if it's greater than 0, we put output 1. If it's otherwise, we output 0. Okay, so let's try to do it. Okay, so given a linear, so basically for the perceptron training, we start with a W, okay, the weight. So here, let's start from 0, 0, 0. Okay, so 0, 0, 0, and the data, the first data is 1, 0, 0, right? So it basically 0 times 1, 0 times 0, 0 times 0, so it's 0. Then the output is 0. Your output is 0, and the answer is 0, so which is correct. If it's correct, you do nothing. You finish the first data. Okay, then the second data is 1, 0, 1. The answer is 1, and currently you are 0, 0, 0. So you do the calculation, your output 0. So you find that you are wrong. The answer is 1, but you are outputting 0. So you are wrong, and you are small. Okay, your output is 0, so you are wrong and you are small. You are small, then you add the data to the weight. So the original weight is 0, 0, 0, and the data is 1, 0, 1, so your new weight becomes 1, 0, 1. Okay, so this will finish one update. Okay, then you look at the third data point. You can check basically it's correct, and then you look at the fourth data set. You'll notice that it's also correct. Okay, so you can see here, we checked 4 data and we did 1 update. Okay, so some terminology, okay. This is also universal terminology. So we call it iteration if we look at 1 data. Okay, so here, that means we completed 4 iterations. Okay, so we completed 4 iterations. Okay, so there's another concept called epoch. Epoch means that you look through all the data once. Okay, so in this case, we finish 4 iteration, means that we finish 1 epoch. Okay, so this is a terminology that you use very often, no matter you are doing machine deep learning training or anything. So usually we are using this terminology. Okay, iteration and epoch. Okay, so if you want to be professional, please use the same word. Okay, because I see many papers they are using iteration to represent epoch. Okay. So there's another term called episode. This is particularly used in RL, reinforcement learning. Okay, so if you are reading some papers, please be careful on these wordings. Okay, so by default, iteration means that you update the parameter once. Okay, no matter here is update or not update, it's once. Okay, so here we have 4 iteration, and then the epoch means that you go through the data 1 time. Okay, so here you can see that we finish 1 epoch, then we need to decide whether we should proceed or we should terminate. So the criteria is that as long as you have updated in this epoch, you should do next epoch. Okay, so here we have updated once, then we should do the second epoch. So you can see that in epoch 1, we already have the weight to be 101, then we move to epoch 2. Okay, then epoch 2, we need to go through the data again. Okay, so here is the iteration 5. In the iteration 5, we look at 100, and now the weight is 101. We calculate it, we find that this is 1, which is wrong. Okay, the data, the answer should be 0, and we are large. We are large, then we subtract the data. So 101, we subtract the data 100, then we have 001. So this finish another iteration. And then we check the second data, we check the third data. Third data we find is wrong again, then we just do the updating. The fourth data we also did this. So here we finish 8 iteration, and we finish 2 epoch. Okay, and in the epoch 2, we also update the weight. Means that we have to move to the third epoch. Okay, then we move to the third epoch. So in the third epoch, you update, you find that you're wrong again, you update, and you don't update, you don't update, you don't update. Okay, then we finish the third epoch. So after the third epoch, because we update in the third epoch, we have to move to the fourth epoch. Okay, so we check fourth epoch, then we find that example 1, 2, 3, 4, we don't all correct. So in this case, we do not need to update anymore, so we can terminate. Okay, after the termination, we find that our final weight is 011. Okay, so this whole procedure is a error correcting mechanism. You can see that it's like you're wrong, you find it wrong, and you update. You find it wrong, you update. You keep learning, and gradually after 4 epochs, you find a good weight. Okay, so this learning procedure is very similar to deep learning training. Okay, so the perceptron is closely related to deep learning. So you can see that this is actually a very typical machine learning method. Okay, so you can see that it's evolving from one epoch to another epoch is become better and better and better. Okay, so this is a very good example of training, a learning process. Okay, so here there are some issue we haven't mentioned. Okay, so usually when you're talking about the learning, it's actually millions of data, hundreds of thousands of data, right? So you have thousands of data in one epoch. Okay, and most of the time we want to do a permutation of the data in each epoch. So you know what is permutation? So permute means that you randomly you just perturb the order of the data. For example, 1, 2, 3, 4, 5. Next time is 1, 3, 2, 4, 5. You just randomly change the order of the data. This we call it a permutation or permute. Okay. Okay. So every epoch we should permute the data. This is to have a better convergence. Okay. So in this example, you can see that I didn't permute the data. I keep using the order 1, 2, 3, 4. But this is actually not good in practice. In practice, we should permute the data. Maybe to help you to better understand what is permutation, maybe I ask you. So here, basically the idea is that we need to provide the data randomly, right? So there are 2 approaches. So one approach is that you do for each epoch, you do the permutation. And there's another approach is that you just randomly select one from data. Every iteration, you just randomly select one from the data. You can also do the training. Yes. So this tool gives you the different performance. Okay. Why? This one thinks too random. Okay. It thinks too random because you may never select some data for a long time. Because this is completely random, right? So you may never select some data for a long period, okay, which is actually not good. Okay, so this one, it contains some randomness, and at the same time, it guarantees that each epoch look at all the data once. Okay, so this is actually a pretty good. This is a I would say it's a delicate choice. Okay, so we add some not randomness in the data, but we ensure that the data is we ensure that all the data is used in the training. Okay, so permutation. So later in, for example, later if you want to train the deep learning model, most of the model will use this idea. Okay, this is called permutation. So basically, you permute. If you don't like this word, in deep learning, usually this is called shuffle. Okay, basically you shuffle the data. Okay, so so last one, this is just a note, and I think it's easy to see that the perceptron may not converge. Okay, if you have a lot of data and it may run forever, based on this criteria, it may run forever. Okay, if it runs forever, usually what we are going to do is that we do some early stopping. Okay, or there's actually another version, means that, so here you can see that what I'm doing is W plus and minus X. Okay, W plus and minus X. And if we think this is too aggressive, what we can do is that we can put a alpha here. For example, alpha can be 0.1. Then the every data, they contribute a little bit less. Okay, so the alpha, this we call it a learning rate. Okay, so this is also a concept in the deep learning. Learning rate means that how much you trust this data. So here you can see that if alpha equals to 1, means that I trust this data a lot. I just fully use this data to update my W. Okay, if I don't trust this data, there are so many data, I don't want to trust one single data too much. I use a smaller learning rate. Okay, I think this is very easy to understand, but just give you the terminology. Okay, so in machine learning, people, I don't know why, but they like to call this a learning rate. In optimization, people usually talking about calling this a step size. Okay, so in different domain, basically people are talking about the you gave different name for different for the same thing. Okay, depending on which community you are at. Maybe you read a paper from optimization, they call this step size. You read a paper from AI, then they call this a learning rate. Okay. Okay, so here is a summary of the steps. Maybe I'll skip this part. Later, if you are interested, you can check. Okay, so this is a learning procedure of perceptron. Okay, maybe let's finish this part and we take a break. This part I think is interesting, and it's actually a difficult part. And if we are doing a master level machine learning, no one will talk about this. Okay, it's complicated part. But if you want to write some paper and show that you have a very good thoughts on your developed AI method, I think this part is particularly important. Okay, we call it learning theory. Learning theory is basically talking about, given a machine learning method, can you provide some guarantee or can you provide some proof on the performance of machine learning? Okay, so machine learning is actually not a very, people saying that machine learning is a black box, but there are a group of people. Usually they are mathematicians and statisticians. They are trying to understand the behavior of machine learning, and they have some theory on it. Okay, so those theory gives you some guarantee. Okay, so here I just give you a very brief idea. So essentially, let's look at the machine learning model from a statistical perspective. Okay, so here is the idea. So if you want to demonstrate the performance of a machine learning method, you have to assume how the data are generated. Okay, so how the data, so basically you need to give assumption of the data that you collected. So here we have some data generating mechanism. Okay, so let's say we have some data that is from a unknown distribution. The X, the data that is from some unknown distribution we don't know, the PX. So basically we generate the data from, so you think of this unknown distribution is our nature or our your system, the domain that you want to study. Okay, so the or you just think of it as our oracle or God. So basically, God creates some data for you, and it's from some distribution we never know, and there's some unknown function. This is some mechanism. Okay, so basically, you input those X into some mechanism C, that you get the outcome Y. Okay, so C is some unknown function that you don't know. Okay, for example, in your task, for example, if you want to do something, then in general there are some, for example, you want to do the wind simulation, say for example, then you input the boundary wind, and then you want to look at how the wind there interact. So this mechanism is actually the computational fluid dynamics, is the Navier-Stokes equation, something like that. Okay, so this is basically something that you don't know, some mechanism, and you input X, you get Y. Okay, so essentially, what you observe X and Y. You observe a lot of X and Y. Okay, X1, Y1, X2, Y2, X3, Y2. You observe a lot of X, Y, but you never observe P and C. Okay, so basically what our objective is that we want to, so a learning algorithm, when we talk about machine learning, is that we want to define a learning algorithm that can find a good function C, for example, or H, such that this H approximate this C hat as much as possible. Okay, so here technically that we want to find, so basically what we are doing is that we want to find a C that achieves the lowest training error. And so basically what we want to do is something like this. We want to minimize the training error H and D train, and we want to find the H from the hypothesis set, the capital H. Okay. So this is our learning algorithm. Okay, but our goal is not this. Okay, so we want to do the in the machine learning training, we are doing this. Then we find the H function. Okay, but what we actually want is that we want to have a H that has a low true error. It's not training error. So it's different. It may be different. Okay. So again, let's. I think you may forgot. So last week we talked about this. So there are a lot of error in the machine learning training. So the first thing is we call it true error. True error is the actual things that we want to look at. So it's basically how your model perform on all the possible data sets. Okay, so this all the possible data sets. Now we have a better definition. It's basically the P star, the GART known distribution. So if the data is from this GART known distribution, and your H should perform the best on this P star distribution. Okay, but this one we never know. What we know is that we have a test error rate. Basically, is to so basically you just leave out some data, then you have the test error rate, and you have the validation error rate. The validation error rate is already a little bit overfitted because you are choosing the hyperparameter for the validation. Okay, and the training error rate is a very optimistic error rate because you are overfitting the data. Okay, so if I ask you to to look at the order, it's actually most of the time the training error rate is smallest. Okay, and the validation error rate usually is larger than the training error rate, but the smaller than the testing error rate. And then the true error rate might be even larger. Okay, so you can see that we can never approximate we can never reach the true error rate, but we are trying to find the one that is similar to the true error rate. Okay. Then let's write some mathematic definition. So this is a textual description. So let's try to write something. Okay. So we define a risk. We define a risk of a function h. Okay. So the RH defines as a risk of this hypothesis or this function h. Okay, and we define the true error. The true error is actually as follows. So you can see that given this x, we put x to the God known function. Usually we have a name for it. Okay, let's call this a oracle. Okay, so you put this x into the oracle, you get the answer. This is true answer, right? And you put this x into h, your own function, you get an answer. If these two answers are different, which means you are wrong, right? Which means this is an error. Okay, so we take the probability, we look at the probability of this happens. So basically, we look at the probability of your being wrong. We define this as the risk. So this is basically the definition of true error rate. Okay, so this is a formal definition of the true error rate. Okay, then let's look at what is actually our doing. We are defining another thing which we call it a empirical risk. Okay, empirical risk we use R hat. What are we doing in the training is that we are looking at so this is the ground truth. This is a y, right? And this is our prediction, y hat. And then we only look at the data, the x from the data. We're not looking at the x from the God known distribution. We only have the data as d, right? So this equals, we just count all the data from 1 to n, how many we are wrong. Okay, so this 1, do you know this notation? 1. This we call it an indicator function. Indicator function. It's basically if this one is hold, it's 1. If it doesn't hold, it's 0. Okay. Indicator function is basically it gives a statement inside the indicator function, and if the statement is correct, then it's 1. If its statement is wrong, it's 0. Okay, so here it basically says if this is correct, means that you are wrong, then we count by 1. Okay, we count this n number of data, and then we take we divide it by n. This is basically the error rate in your training. Okay, and in particular, the oracle answer is actually yn. Right, so this is basically what you are doing in your training. Okay, so you can see that in your training, you are minimizing the empirical risk instead of the actual true risk. Okay, so you want to find a h based on the empirical risk. Okay, so that's why most of our training we call it a empirical risk minimization. So most of our training is called empirical risk minimization. Okay, so here you can see that we have an assumption that the empirical risk is quite similar to the true risk. Otherwise, you are doing what you are doing here has nothing to do with the true risk. Okay. Okay. So here you can see that so here we have a true function, right? And then we have what we want to have is this one. We want to have this H star. H star is that we actually minimize the true risk. This is expected risk minimization, but this one is not possible because we don't know RH. Okay, so instead we are doing empirical risk minimizer, which gives us a H hat. Okay, so H hat is basically here you can see that we do see a discrepancy. So we know H hat. Okay, we using our learning algorithm, we know what we can find a H hat, but how can we guarantee that so there are multiple guarantee, okay? So first thing, can we guarantee that H star is similar to C star? Okay, second thing, can we guarantee the H hat is similar to H star? Okay, so if we can guarantee these two things, then our learning algorithm can finally find the true function C star. Okay, so this is a whole idea of analyzing a machine learning algorithm. Okay, so essentially, how can we make H star equals to C star? It's actually related to this. Okay, so basically you are finding the minimization from a set. What if C star was not in H? Okay, so in that case, you will never find the H star will be definitely different from C star. So in that case, H star will be definitely not C star, right? So basically it's here. You think of the H something like this, and your C star is here. Maybe you just find H star here. Okay, so there is a gap. So why this happens? This happens because you misspecify the hypothesis set, right? You didn't provide a good hyperparameter. Okay, so we call this is one source of the error. Okay, and if the C star is in this hypothesis test, it's still possible that your empirical risk is different from the actual risk, and then your H hat is different from H star. Then it also gives you the different answer. Okay. Okay, so let's assume that we have a super good learning algorithm that we can definitely achieve this. So it means that we can achieve almost zero training error. Okay, so this is most of the time it's easy to achieve, right? So now you have a very good H hat. So basically the learning theory gives you some bound or give you some definition how the H hat is close to C star and close to H star. So basically there's a group of theory doing this. Okay, so we call this a learning theory. It's actually very complicated. I'll just try to give you a very shallow flavor. Okay, so very simple or usually when we talk about learning theory, the first thing we're going to talk about is called PAC learning theory. PAC refers to probability approximately correct. Okay, so PAC basically PAC theory want to give you some guarantee like this. Okay, so basically it says that the probability of the model that you get, the probability of this empirical risk is very close to this true risk, close to this true risk by epsilon, and the probability of this is greater than 1 minus delta. Okay, so basically it says that there's a high probability that the empirical risk is close to the true risk. Okay, I'm not sure. Have you learned the epsilon delta language? I guess no. Have you heard about this epsilon delta language? Okay, no. This is a very commonly used approach when you want to prove something. Okay. So usually this will be taught in mathematics analysis, 数学分析, in your year 1 if you're a mathematics undergrad. But if for engineering students, usually they will skip this part. Okay, but if you want to read some serious AI paper, you will see a lot of epsilon delta language. Okay, application paper you already know, but if you read some paper that is AI paper, theory, the AI plus theory, then you will see a lot of epsilon delta language. If you're interested, just search this and try to understand what is an epsilon delta language. Okay, so here is a very typical epsilon delta language. This basically says that for some epsilon, then you have some probability. You can have some probability that you can define a delta such that these two are very close. So basically, epsilon delta language is to help you to translate some description to mathematical equations. Okay. Then basically we have something that we need to discuss. So basically to guarantee this, we need to have different assumptions, different settings. So here we need to differentiate two settings. The first setting is about H. As I just mentioned, C star might be in the H and might not be in H, right? So here we call it, if it's in H, we call this a realizable. It means that we can finally find the true function. Okay. If we don't know whether it's in H or not, we call this agnostic. Okay. So basically it's a more general case, but it's more difficult. And we can look at the H, whether it's finite or infinite. Okay. I'm not sure you know what's this mean. This is called cardinality. Have you heard about this? It's basically number of elements in this set. Number of elements. For example, if the number of elements is finite, then basically this set has finite number of candidates. Otherwise, it's infinite. Okay, so infinite, for example, linear regression is infinite, right? Because beta is arbitrary, right? Decision tree, I guess, is finite, right? So the hypothesis set for decision tree, I think, is finite if you set the less. Okay, so basically the candidate that you choose, you can be finite as infinite. So basically you can see that there are 4 different combinations. So you can, so given H is realizable and finite, and given reliable and infinite. So basically there are 4 different combinations, and given different combination, you can write some proof. Okay, so I think you can definitely find what is the simplest one. Basically, it's realizable and finite. Okay, so here is some theory. I didn't give you the full proof. It usually takes 1 week to discuss that. I just give you a flavor. Okay, so here let's talk about the simplest one, finite and realizable case. Means that C is in the H. C star is in the H, and there's an arbitrary distribution P star. Okay, so here we says that if your training data has this many. It has this many. M is the number of training data, right? If your training data is greater than this number, then we believe that the then with this odd with, so basically we will have if your training data is this, and then our training error can be 0, then we can prove that your true error rate smaller than epsilon. So basically, translated to language is that if you have sufficient number of data, then and also if your training is very sufficient, then we can guarantee that your testing is also small. Okay. So given this, so here you can see that we can, so basically given this theorem, you can write a inequality like this. So this basically says your true error is smaller than this number. And you can see that if the number of data increase, the true error will decrease. So this basically demonstrates that if you have sufficient number of data, and if you have more and more data, then your training error, and this is not training error, this is testing error or true error will reduce. This gives you the foundation of why the big data, why the learning is useful. Okay. I guess I was I skipped the proof. It's actually pretty complicated. Okay, so there's another case is finite and agnostic case. If it's finite and agnostic case, you can see that this equation, this inequality is a little bit different, and you can prove that this one is larger than that one. Okay. And also, this one, we cannot prove the true error goes to 0. We can only prove that the true error is closer to the training error because it's agnostic. Okay. And then you can see you have something like this. So your true risk is basically the training error plus something. Okay. So for if you want to publish some AI paper in AI related journal and conference, this type of derivation is very important. Okay, at least you should have some analysis of the AI method that you developed. Okay, so that gives you some understanding. Okay, and also it makes your paper not just a trick; it's more like a methodology. Okay. Okay, so if you are interested, I will highly suggest you look at PAC learning theory. It's basically PAC, and there's another and there's other I haven't mentioned, but I just put the name here. One thing is called VC dimension. This is actually a very important concept. VC dimension help you to identify the complexity of a problem. Okay. For a complete machine learning lecture, usually they will talk about this one. This one is quite difficult to understand. So you can, if you're interested, just look at some lecture note, look at some lecture video online. Okay, VC dimension. In Chinese called VCV. Okay. So you can see that there are quite a lot of theory that tries to guarantee that you are learning the correct things. Otherwise, it's just arbitrary machine learning. You just have X and Y, you just randomly learn. Okay, so there are actually a lot of design in the machine learning algorithm to ensure that you are learning the correct answer. Okay. Okay, so that's it for lecture 8. Maybe let's take a break. We move to more methodology on unsupervised learning. Okay, so let's take a break. Okay, so let's move. Maybe let's move on so we can finish early. Okay, so one thing, the homework has been released. Okay, so please go to the Blackboard and you will see the homework. So I intentionally put some mathematical question for you. And I highly suggest you don't just directly use the ChatGPT, because basically if you input the question into ChatGPT, it can directly give you an answer, okay? I cannot give you the question that cannot be answered by ChatGPT because that would be too difficult, okay? But you just try to spend some time to try to prove something by yourself. Which is important. If you really want to learn machine learning, it's actually learning the mathematics. Okay, so if you are saying that you want to learn AI, indeed, everything basically is optimization, statistic, and mathematics. Okay, so if you just want to apply AI, you cannot publish good papers. Okay, so if you really want to go into this area, you should practice your mathematic capabilities, in particularly understanding those complicated notations. Okay, because most of the paper you see from AI domain, it has very complicated notations. Okay, so you should give you the chance to try. And of course, you can try to use the generative AI to give you some answer, but you should understand at least the results. Okay, so the due for the homework will be end of this month. So please try to do it. Okay, so the quiz is closed book, and there will be some similar question like that. That's okay. So please just get yourself prepared for those notations and equations. Okay, so you should get familiar with reading the equations and notations. Okay, because most of the paper you're going to read in this domain is full of this. Okay. Okay, so then today, so we move to the lecture 9. So so the title is unsupervised learning, but actually we're also giving you some other concepts. Okay, so let's start from the one that is one of the unsupervised learning approach. So when we talk about unsupervised learning, I think we mentioned two. One is called clustering. Another one is a dimension reduction, right? I think I'll highlight. I'll talk more about the classroom, but dimension reduction maybe I'll leave to you for learning. Okay. So the clustering so basically you're given a data matrix. Okay. So what we want to do is that we want to find the closest data. We want to group them together, and for some data like this, we group them together. Okay, so essentially clustering is trying to split the data into groups, okay, or we call it clusters. And within this cluster, they are similar. Okay, so basically this is useful to organizing the data, and also is useful to discover some pattern of the data. Okay, and this is also useful for some pre-processing. So basically you can cluster the data, then you know the pattern. You can find the representative data from each of the cluster. Okay, so so in the classification, so here we are talking about a similar and not similar. Means that we need to have a definition of the similarity or dissimilarity. We call this a distance measure or similarity measure. Okay, distance measure is measuring the distance. The similarity measure is measuring the dissimilarity. Sorry, measuring the how they are close or how they are far away. So it's the other way around. Okay, so here you can see that if the data is a vector, then we can easily define some Euclidean distance and Manhattan distance. I think I already gave you this notation. So this now I think you can read what's this meaning. The meaning of this is basically one vector subtract another vector, and then you look at the square, sum of square, and take the square root. So this is two norm, right? This is two norm. This is one norm. So basically, you can see that we're measuring the vector distance by the p norm. Okay. And then given this p-norm, we can present you the first algorithm, which is called k-means. K-means is a very popular and famous algorithm for clustering. If you want to do clustering, usually most of the people will choose k-means as the first choice. I think the main reason is simple. Okay, it's simple and it's simple and also it's effective. It's pretty results most of the time is pretty good. So people like to use this, have a try. And here I'm going to give you a optimization perspective for this k-means. So basically k-means, first thing for k-means is that you have to assume a k. A k is a number of clusters. Okay, number of clusters. So this is actually a weakness of k-means. Basically, you have to give me the number of clusters before clustering the data. Okay, so for example, you just give me a number 3 or 4, and then what I'm going to do is that I will give you the center of the cluster and which data belongs to which cluster. Okay, so here I'm using a notation called mu and z. Z is from 1 to n. Okay, so this is the belonging, representing the belongings. So basically Z1, this belongs to K. So this is also another notation. This refers to 1, 2, 3, 4, 5, all the way to K. So basically Z1 needs to choose one cluster that it belongs. And mu1 and mu_k is the center of each cluster. Okay, clear? So you have K cluster, so you have K centers. And Z is basically an indicator, indicating that the X1 goes to, for example, 3, X2 goes to 4, something like that. Okay, so here, this is a vector, and this is an integer. This is integer. Okay. Okay, so what we want to do in the clustering, so we can write a objective. The objective that we want to make sure that each of the data xi is closest to its center. So here you can see the notation is zi. So zi is here. It's basically the index, and then mu zi. So basically, it's a belonging as a center that the xi belongs to. Okay, so we look at the distance from xi to its center, and then we measure their distance, and we sum for all the data. Okay, so this is the total distance between the data and its center. Okay, so this is our objective. So we want to minimize this. So by doing this, we actually will make sure that each of the data, they are clustered together. Okay, so how do we solve this objective function? So basically, we want to reduce, we want to minimize, right? So we want to minimize, and what our decision variable is all those. We can change the center location. We can change the belonging of each data. Okay, so here, just curious, do you know what is gradient descent? I think yes. Yes. I think Professor Jiang should talk about this. If he didn't talk about gradient descent, then how do you solve logistic regression? Do you know how to solve the logistic regression? Okay, so maybe I just use one slide to talk about this. So given for example, given an optimization problem like this, we want to find x such as fx is the smallest. Okay, so there is a universally good approach, which we call it gradient descent. So the idea is very straightforward. You just give me a x0, and I can keep iterating. So the iteration approach, the iteration principle is as follows. It basically is partial f partial x alpha. Okay, so I can illustrate from a figure. So here, for example, your starting point x0, and then you take the derivative at x0. Sorry, I should write like this. You take the derivative at x0, and then this points to this. So basically, this point gives you the gradient, right? So the gradient is something like this, and you want to make use this direction, and you update x. So the x1 is here, then x3 is here. So gradually, you can see that we can move to the minimal point. So this we call it a gradient descent. So gradient descent is the equation is like this. This is updating rule. Okay. Xn plus 1. So next iteration equals xn minus some the gradient. And here we have a alpha. I think now you know the name for alpha. This is called learning rate. In optimization, it's called step size. Okay, in machine learning, it's called learning rate. Okay, so this we call it a gradient descent. And here, remember that x is a vector. Okay, so here is a vector, and this x is also a vector. Okay, so here you have a vector. This is also a vector, and the gradient of so derivative of f with respect to x, this is also a vector. So it's a vector minus vector equals another vector. Okay, so everything this here is a vector. Okay. So this is gradient descent. Gradient descent, usually we call this a first order method. First order method. This is pretty useful for finding the minimum point. Okay, so here you can see that if you are here at the minimum point, then the gradient becomes 0. This becomes 0. If this becomes 0, then you become stabilized. Then your algorithm can finish. Okay, so so basically, this is very commonly used, and also this is the underlying mechanism for deep learning training. Okay, deep learning training is also using gradient descent. Okay, so this is a standard gradient descent. So here we are talking about another one. We call it coordinate descent. Okay, so this is actually a variant, a modified version of gradient descent. So again, you can see that the approach. One thing I also want to mention that gradient descent is particularly designed for we call it unconstrained optimization. Means that you should have the x is free. It can be any it can be real numbers. If x has some constraint, then goes to another domain called constraint optimization. It's completely different. Okay, gradient descent is only useful for the unconstrained problem. Okay. So here is also, you can see here is also an unconstrained problem. We just want to minimize j theta, and we want to find the optimal theta. Okay, so there is this is actually a modified version of gradient descent. In the gradient descent, you can see here, we update all the x at the same time. So x is a vector, right? Then coordinate descent basically says that there are multiple coordinates. Every time we only update one coordinate. So here you can see that we just pick one variable and then minimize it. Okay, so if you think of this whole diagram, so you can see that the updating procedure, this is a two-dimensional problem, right? So you can see that the updating procedure is something like this. Okay, so here from theta 0 to theta 1, we only modify theta 1. And from this one to this one, we only modify theta 2. And here we only modify theta 1. So here you can see that the coordinate descent, every time we only update one. So in this case, we have a theta 1, theta 2. We have two variable. Okay, so the coordinate distance says that you don't need to update theta 1, theta 2 simultaneously. What you can do is that you can update theta 1 first and theta 2 second, and then you just iteratively update this two. This also gives you a good result. So do you have an idea why we want to do this? So you can so basically if you are updating theta 1, you will view theta 2 as known. Okay, and then when you calculate the derivative, it becomes much simpler. Okay, so previously you have to calculate the two-dimensional derivative. Now it's just one-dimensional derivative. It's much simpler. Okay, so usually, given some particular problem, you notice that it's difficult to calculate the full derivative. Maybe coordinate distance is a good option. Okay, so you know the coordinate distance, then there's another modified version, which is called block coordinate distance. This is also very straightforward. It's basically you're given a vector, you can separate them into blocks. And then every time you update a block, so it's straightforward, right? Coordinate distance is just one variable. Gradient distance is a full variable. Block coordinate distance is in the middle, part of the variable. Okay. So here I just use alpha and beta to represent. So here you can see that I have alpha and beta, and then I want to do a minimization. So what I can do is that I can iteratively choose alpha and beta to do the gradient descent. And then when we update alpha, we keep beta fixed. When we update beta, we keep alpha fixed. Okay. So this block gradient coordinate descent, so basically I think it's straightforward to understand, right? It's just a modified version of coordinate descent. Okay. Okay, so why we're talking about this? Because you can see that for k-means, it's very clearly you have two parts of the variable. One part is mu, another part is z. Right? So what you can do is that if mu is fixed, means that if the center of the data is fixed, okay, then basically what you are going to do is that you just try to find k, you just try to find which center the data is close to, right? You just try to find which center the data is close to. Given xi, which center the data is nearest, okay? And if the z is fixed, means that each of the center is each of the data we know how where it belongs to. Then here you can see that we just try to find the mu, which is that we try to find the center. Okay, given all those data, how to find the center? You don't need, so this here you can see this is an optimization problem, but this optimization problem is super simple to solve. You can get a closed form. So maybe the question, given 3 points, so this is x1, y1, this is x2, y2, this is x3, y3. What is the center? The center is x1 plus x2 plus x3 divided by 3, y1 plus y2 plus y3 divided by 3. So this is center. So here you can see that you just sum all the xi that belongs to k, and then the number of nk is the number of data in k. So this directly gives you the center. Okay, so you can see that by decomposing the objective into two parts, you find that this problem is much more simplified. Okay, in the previous one, it's very difficult to solve. If you want to directly solve this optimization, it's almost impossible. But if you assume part of them are known, you'll notice that another part is also easy. Okay, so then this gives you the clustering algorithm, k-means algorithm. So essentially, what you are going to do is you just repeat two things. You you believe that each of the center is fixed, and then you assign the data, and then you look at you fix the assignment, you calculate the center. Okay, so I quickly give you an example. Okay, so here you can see that I'm doing k equals to 2. And this is a 2-dimensional data, d equals to 2. So those each of the dot is one data point, and I randomly give you a center at the beginning. Okay, so you just iteratively do these two things. The first thing is that you assign each data point to the closest center. How do we do that? For example, this data, we can measure the distance to red and measure the distance to blue. We think this is black. This is red, right? Close to red. So how can we find all the data? You just connect this to, you find the middle point, draw a perpendicular line, right? So all the data here should go to red, and all the data on the other side should go to blue. So it gives you this one, right? Then we know these are blue, we know these are red. So we do the second step. The second step is that we can recompute the center. The recomputing the center is also straightforward. You just take the average. Okay, so here you can see that roughly, I think the center for red is here, and the center for blue should be somewhere here. Then you have this one. Okay, then we repeat. You just look at the center and take the perpendicular line, and this should be red, this should be blue. Okay, then you have this one, and then you recalculate the center. Okay, that gives you this one. Okay, you just keep updating, then eventually you can see that this separates the data. Okay, so underlying mechanism, you can see here, this is a block coordinate distance. But from this particular problem, it has a physical meaning for each of the steps. So you can see that the procedure is super straightforward, and you don't need to solve anything. You just compare the distance, and then you just calculate the average. You just keep doing these two things, you finish the k-means algorithm. Okay, this one is pretty powerful actually. So here I just summarize some pros and cons. So you can see that this is super simple, but many cases the performance, the final result is actually pretty good. Okay, if you read papers, you definitely see many people are using k-means. I think one reason is that it actually gives you some good results. Okay, and also this is you can see that the whole algorithm has nothing to do with the dimension of the data. Okay, because you just calculate the distance, that's it. So this is actually agnostic for the high dimensional data. So it's actually regardless of the data dimension, the algorithm does not change. Okay, and also there's a theoretical proof I don't need to mention here, but this guarantees to converge. This will definitely converge after several iterations. Okay, so there are some disadvantages. There are two main disadvantages. The first one is that you have to choose k before running the algorithm. Means that given a data, you have to guess how many clusters are there. Okay, so this is a main issue for k-means. And there's another one is that actually if the initial center changes, maybe the final result will change. So we basically call it sensitive to initialization. Okay, but this one is easy to solve. You just run multiple times. Okay, so the issue is this one, k-mean. You have to choose k. So there's a standard approach to select k, which we call it an elbow method. So the elbow method means that you just run the k-means for all the k. Okay, and then you draw the objective. This is objective. I think you can prove that. I think you can prove that for this objective, given k becomes larger and larger, this objective will become smaller and smaller. So I think you can prove this. Okay, so this objective will definitely decreasing when the k increase. You can imagine that if k equals n, then this becomes 0. Okay, so so essentially you have some decreasing curve given different k. So you can see here in this figure, K is a x-axis. So you draw the objective, then you will have something like this. So this will goes to almost goes to 0. Okay, so the elbow method says that we want to find that we want to find the K that gives you the most efficient decrease of the objective. Okay, so here basically you can see that for this part, the slope is actually still high, so it's still steep, means that the objective reduced quickly. But after here, after this area, you can see that the increasing the K is not very helpful. It's just help a little bit. Then we think that K, you may choose K around this area. For example, 6 or 7 or 8 should be okay. Why this is called elbow method? So you can think of this as your arm, and you choose the location of your elbow. Okay. I think it's also easy to justify. Okay, so you can imagine this part is more like an overfitting. Okay. Again, so one thing also to mention. So here you can see that we also have a parameter to tune between overfitting and underfitting, and this parameter is K, right? K is small, underfitting. K is large, overfitting, right? Okay, so I quickly go through this part. So in the k-means, you'll notice that each of the data is assigned to a center. So this is a hard assignment, right? So it's 100% belongs to one center, right? If do you think if it's possible that we can have a soft assignment, or we call it probabilistic assignment? Means that given this data point, we believe that is like 70% to this data and 20% for this center. So we call this a soft assignment. Okay, so in the past, your Z is something like this. If you still remember, this one is called a one hot. Your Z is actually a one hot variable, basically indicating that this belongs to the second cluster. And we can relax this a little bit. We can see that this is 0.8 and this is 0.2. Okay, it becomes a probability. So here we define a pi k. Pi k is basically a probability of, so basically it gives you the probability. Okay, so this we call it a soft assignment. Okay, so once we have this soft assignment, this corresponds to another clustering algorithm, which is called GMM, Gaussian Mixture Model. Have you heard about this? Yes? No? In Chinese, it's called 高斯混高斯模型. Okay, Gaussian mixed model basically, so in the k-means, it basically says that everything belongs to this data point. In the Gaussian mixture model, basically says that each of the cluster is a Gaussian distribution. It's a normal distribution. Gaussian is basically normal. Okay. Okay, so here you can see that if we have three clusters, then we have three Gaussian distribution. Okay, mu and sigma. You know what is Gaussian distribution, right? So normal distribution, mu and sigma, right? So why we call it Gaussian distribution? Usually it's multidimensional. So it's high. I don't know why people just call it Gaussian. Okay. Okay. So so you can think of the data. So we believe that the data comes from the data is sampled from those Gaussian, this three Gaussian distribution. So here we have two things. One thing is that you should give me a pi k, indicating the probability of choosing one specific Gaussian distribution. So here you can see I have three Gaussian distribution, right? The pi, this gives you a vector, for example, 0.2, 0.7, 0.1. This basically says that I have 20% chance to choose the first Gaussian distribution, and I have 70% chance to choose this distribution. Okay, and given, so first you choose a distribution, Gaussian distribution, and then you sample a data from this Gaussian distribution. So you sample this X. So you can imagine that this X is actually sampled from 3 different Gaussian distribution with different probability. Okay, those data mixed together, that gives you the original data. Okay, so what you want to do is that given those data, you want to recover the 3 Gaussian distribution and also the probability. So here you can see that what we want to know is we want to know the probability for each Gaussian distribution, and we want to know the mean and standard deviation of each Gaussian distribution. Okay, so here you can see that we don't have a hard assignment. The hard assignment previously Z is replaced by pi. Pi is a soft one, so it's just a probability. Okay, so then because this is a probability problem, then I think you'll learn MLE, right? So Professor John definitely talk about MLE. So then you can write MLE. So this is a normal distribution. It's very easy to write MLE. Okay, so very straightforward. So here MLE says that given the data, you write the data. You write the probability for those data, right? You have data from X. The data is X and Z. Sorry, you only know the X, but you don't know the Z. Z is basically which data. For example, you sample. So here, this is a 2-step, right? So first thing, you sample based on pi, which distribution you want to use. For example, I sample. I want to use the second distribution. Then I sample from the Gaussian distribution from this one. Okay, so here you can see that the first one we call it Z. So basically, which distribution you sample from is Z, and then from the distribution you sample X. So here you can see that we have X and Z. Okay, in reality, we don't know Z. This one is unknown. Okay, we only know X in the data that we have. But let's first write the likelihood function. So we call this a complete likelihood. So basic complete likelihood, I think it's very easy to write. You just take this is log likelihood, so log multiplication of p. So you change the log to here. You change the production to some summation, and this is p. And this p is basically you use a condition. So first you look at the what's the probability that you select this Z, and then given this Z, what's the probability of X? So you just iterate over this pi, iterate over this K, and then eventually you get this, okay? And then so eventually you get this one. So this one is straightforward, right? So later, if you don't know how to derive, just try to practice, okay? So this is very standard procedure. But our case is that we only know X, we don't know Z. Okay, in that case, you can also write the whole, so basically you just marginalize the Z. So here you can see that we sum over Z. This we call it a marginalization. Okay, we just sum Z because we don't know Z. Okay, then this also gives you a likelihood. This we call it a marginal likelihood. Okay, so in this case, we cannot do a complete likelihood. We can only do a marginal likelihood because we don't know Z. Okay. Okay, so this is so basically we are doing a max MLE, so it's a maximization problem, right? So essentially, what are we solving? We are doing a maximization problem, and the decision variable include pi, mu, and sigma, all the k, such that we want to maximize the log likelihood of theta condition on. So the theta is basically these things, condition on data. Okay, so this is our what we want to solve, MLE, right? So if we want to do MLE, so there's some issue. So one issue is that this is not free optimization. This is not unconstrained. For example, we have a constraint that's the sum pi equals 1. Okay, and we have another constraint is that the sigma k should be semi-definite positive. Do you know this? Semi-definite positive. You know this? Yes. So basically, sigma k is a covariance matrix, right? Covariance matrix has to be semi-definite positive. Semi-definite positive means that its eigenvalue should be non-negative. Okay, so this is a requirement for the normal distribution. Your covariance matrix should be semi-definite positive. The notation is something like this. My drawing is not very good. It's something like this. Okay. Okay, so this is a requirement for the normal distribution. So it means that your matrix should have some property, otherwise it cannot be a covariance matrix. Okay, so you can see that this is a constraint. It's difficult. Actually, it's difficult to solve. Okay. So here is the summarization. So you can see that we assume they are k Gaussian clusters, and we have those parameters that we want to find, and our objective you already write it. So we want to solve this problem. Okay. So here we are introducing a important concept. So this is widely used, which is called EM algorithm. Have you heard about this? EM. You will definitely use this or read something related. EM refers to expectation and maximization. Okay, so EM algorithm is designed for JMM, but actually recent years you see this everywhere. Okay, so this becomes a protocol. Okay, so basically people, if you find something that is difficult to solve, EM may be helpful. Okay. So the EM algorithm is actually straightforward. It's similar to the k-means. The idea is that you just assume one known, and then you update another one, and you assume another one is known, and you update this one. Okay. So here you can see that. So here basically we says that if we know the z, then everything becomes simple. Okay. The issue is that we don't know the z. Okay, we don't know the z, but we can have a best guess of z based on pi. Okay, so essentially what we can do is that we can use pi to guess a z and use z to update the distribution, and then we update pi. Okay, so here you can see that what we are going to do is that we want to iterate between updating our best guess and updating the parameter. So every time we do a best guess, and then we update the parameter. So the best guess becomes a surrogate or becomes a proxy. So it can help us to largely simplify the problem. Okay, so let me give you more explanation on this. So basically, the EM algorithm is decomposed into two parts. We call it E step and M step, expectation and maximization. Okay, so in the E step, it's very straightforward that you just fix all those parameters, and then you can decide which each of the data which cluster it belongs to. Okay, you decide the expected assignment. So later I give you more explanation. Okay, so once you decide the expected assignment, then basically the assignment is fixed. In the M step, assignment is fixed. Then you just update the parameter. Okay, so this reads very similar to the k-means, right? So actually, this is also a block coordinate descent. This is ascent, so it's same. Okay. So mathematically, this is a block coordinate ascent on a lower bound of the marginal likelihood function. So there has some proof. If you are reading some book, they will give you a proof why the EM algorithm will work. Okay, so maybe I give you more detail. So the E algorithm, the E step basically tries to assign the Z, and basically can calculate the probability of different clusters so that you can eventually find which cluster it belongs to. And then M step is basically updating the pi, mu, and updating the three. Okay, so these are closed form. You don't need to solve an analytical. You don't need to solve optimization. Okay, so similarly to the k-means, so it becomes simplified, so it becomes closed form. Okay. Okay, so then then using the EM, you can solve solve the GMM. So basically here you can see that we initialize all those parameters, and in the E step, we just assign the data to each cluster, and then we update all the parameter. We just keep repeating this two, then we get the result. Okay, so let me give you an example. So here are all the data. So each of the dots, each of this refers to one data point. And here you can see that we have three clusters, three Gaussian distribution. Okay, so how do we calculate the probability here? So basically, let me give you an example. For example, this one. Let's talk about this one. So this one, if it belongs to the green, if it's green, then we can calculate the probability density given it's green. Okay, and it can also be in red. So for this data, you don't know which Gaussian distribution it can sample, right? Because the Gaussian distribution can sample all the support of Gaussian distribution is real numbers, right? So for this data point, it can be sampled by any of these three Gaussian distribution, right? So the probability of it being sampled by the green, we can calculate a number. The probability of this data being sampled by red, we can calculate a number. And the probability of this data being sampled by blue, we can calculate a number. And from its location, I think we can roughly estimate that there are high chance is sampled by green, and a fair chance sampled by red, and low chance sampled by blue, right? So you can see that's how you have these three color on this data. So for this data, there's a high chance. So you can see most of the color is green because it has a high chance that is sampled by green. So if its high chance is sampled by green in the E step, we just think it's green. Okay, so in the E step, we just choose the dominating color. For example, this one is red, this one is blue, this one is blue. Okay, in the E step, we just use the maximum, the largest color to assign it to the corresponding cluster. Okay, so based on those cluster, we can calculate. So we assign all those to be red, green, right? So based on the green, we can calculate what is the center, what is the standard deviation, right? We can calculate all those things, and we can calculate pi. Pi is basically, for example, these are green, these are red, and these are blue. Basically, you just count the number. The proportion of the green is the pi, right? Okay, so update the pi. So those are the updating rule. So here, you can see that the pi is the number of green over the total number of data, and the mu is basically the average, and covariance matrix sigma is basically this one. Okay. And also, everything should has this probability. Okay. Okay, so you update this, and then you have the new data. Then you have the new new parameter. Then you can recalculate the color for each of the dots, and then you reassign in the E step. In the E step, you reassign, then you recalculate the center, recalculate the covariance. You just keep doing this. Okay, then you gradually see that they become, so eventually it becomes something like this. So you can see that finally I find three Gaussian distribution, And I believe those data from this Gaussian distribution, this data from this Gaussian distribution, this good data from this Gaussian distribution. Then I finish clustering. Okay, so this is a soft version of clustering. This has more probabilistic sense. Okay, called GMM. It's actually pretty useful. I think you definitely read some paper using GMM. If you want to have some probabilistic interpretation, this one is better than k-means. Okay, so from the GMM, please remember the EM algorithm. This is very useful. Okay, so in many cases, you find that this is super difficult to solve. Then you can have a guess, and then you update your guess. So this is basically the EM algorithm. Okay, and the EM algorithm has very rigorous theoretical proof that it will work. Okay, I'll skip that proof, and so please check on the textbook. There are a lot of theoretical guarantee for the EM algorithm. Okay. Okay, so we just finished the unsupervised learning. We don't talk about dimension reduction. Because we have next week will be our last lecture. So I think next week is the last lecture because then we have some presentation, right? And we also need to do a quiz. So here I just try to give you some commonly used methodologies. So there are two types of methodology. So this is not a machine learning algorithm. This is more like a schema, okay, called bagging and boosting. Have you heard about this? Bagging or boosting. Okay, so bagging and boosting comes from a concept. We call it ensemble learning. Okay, so the ensemble learning basically the background or intuition is like this. So in the old in the past there was a experiment. So basically they give you a call and then ask a lot of people to guess what is the weight of this call, and then after the average of a large group of people, they find that this average is actually very close to the reality. Okay, so this basically means that even though each of the person, their performance may not be that good, but if you take the average, you make them to vote, the final result is actually pretty good. Okay, so in the machine learning, this gives you we call it a ensemble learning. Okay, so ensemble learning, the key idea says that if we have a lot of weak learners, we can combine the results of all those weak learners so that we can get a strong learner. Okay, so say for example, the SVM, the linear regression, logistic regression, decision tree, those to us is weak learners. It's actually very simple mechanism. It's just very simple. So those are all weak learners. How do you use weak learner to solve a real problem? Usually you have to use this ensemble learning. So ensemble learning basically says that if you can organize a group of weak learner, it will give you a group. Then you will have a strong learner. Okay, so this is a key idea for the ensemble. That's why it's called ensemble learning. So basically you are ensembling a lot of learners here. Okay, so this is example. So here you can see that this is a reality. So you do the weather prediction. Maybe some of the learner are wrong. So you can see that each of the learner, sometimes it's good, sometimes it's wrong. But if you have 5 learners together, you do a voting, then you can see that all the time it's correct. Okay, this has some theoretical guarantee. So as long as your learner has, for example, if you are doing a binary classification, as long as your learner has some capability, means that the classification error is higher than 50%, then given sufficient number of learners, you'll get the good, you'll get the answer. Okay. So this is the idea of ensemble learning. So for the ensemble learning, usually there are 3 different ideas or 3 different approach. We call it bagging, boosting, and stacking. Okay, so these are 3 type of ensemble learning approach. Okay, so bagging, boosting, and stacking. Okay, so I think most commonly used are bagging and boosting. So today I just talk about bagging and boosting. Okay, so maybe I just talk about bagging. So one of the very representative methodology for bagging is random forest. Okay, so this one I definitely heard about because it's super high performance. The reason why it has a good performance is mainly because of this bagging. Okay, so bagging basically says that if you have a lot of decision tree, for example, you have a lot of weak learners, and essentially we have some theory says that if you have B number of random variables, and each of the random variable has a variance of sigma square, and what is the average of the X? So if I take the X of all those X, the average of those X is sigma square over B. So you can see that you here you have B number of results. If you just take the average, then magically you'll find that the variance reduced. Okay. So the variance reduced means that, for example, your answer is so basically you for example you predict something, but it has a high variance. And if you have multiple predictors and you combine them, then you have a high confidence. Okay, so this is a mathematical foundation for the ensemble learning. Okay, then we talk about the random forest. So random forest, basically we are ensembling the decision trees. Okay, from the name, I think you can definitely understand, right? Random forest basically is a lot of trees. Okay, so random forest is actually using 2 ideas. One is called bagging, another one is called split feature randomization. Okay, bagging is actually a short name for bootstrap aggregating. Bootstrap aggregating, this is a full name for bagging. I don't know why they call it bagging, but yeah, they just pick some number, word, pick some character and make it bagging. Okay. Okay, so let me explain what is bootstrapped aggregating. So bootstrap aggregating, so there are 2 things. What is bootstrapped? What is aggregating? Do you know what is bootstrapped? This is a statistic concept. Bootstrap in Chinese is called 重抽样. I think Chinese is very straightforward to understand. Okay, bootstrap basic. Sorry. So let's talk about bootstrap first. Bootstrap basically says that given a data set, what you can do is that maybe you don't need to use this data set all at once. What you can do is that you can replace some of the data by some existing. For example, here you use multiple 1. So basically, you resample the data with some replacement. Okay, so here you can see that you only have 1 data set for the training. And here, remember that we want to have multiple learners, right? So what we can do is that we can bootstrap the data from the original training data so that we can have multiple bootstrapped sample. So in this bootstrap sample, you can see that maybe you have multiple 1, but you don't have 3. And this one you have multiple 4, but maybe you don't have 1. So each of the data set is a sample from the training data with some replacement and duplication. Okay, so here you can have multiple data set. That is sampled, or we call it bootstrapped from the training data. Okay, for each of these new data sets, you can train a learner, you can train a decision tree. So here you can have infinite, you can have as many decision tree as you want. Right? So each of the decision tree, you can see here, we only have a subset of the training data. We're actually training the data using a subset. So here we are generating multiple decision trees by changing the training data using the bootstrap. Okay, so this is easy to understand, I think. So then after we're training, we do a aggregating. Aggregating is simple. You just do a average, for example, or you do a majority vote. Okay. So this is bagging. Bagging is basically you train with bootstrap data, and then you train multiple, and then you aggregate by majority vote. This is bagging strategy. Okay. So you can see that this applies to all kinds of machine learning method. You give me a machine learning method, I can give you a bagging version. Okay. And there's another idea in the random forest, is basically called split feature randomization. This is also very simple. So original data, for example, you have 6 features. I train this data only using 3 features, for example. And I train another decision tree using another 3 features. I just randomly choose 3 features. Okay. So, so in addition to sampling the data points, I also change the columns. I just discard some columns. Okay. So you can see that so basically what random forest is doing is that you change the data set by bootstrapped and also by feature randomization, split feature. And then you train multiple decision tree. And then you just do a voting. And from experiment, later you can also try by yourself. You'll find that the random forest has a very significant performance improvement. Okay, random forest has a very good performance. Okay, comparing to decision tree. Usually you'll train like 200 and 300 decision tree for a random forest, and in most of the cases, I would say like this: in most of the engineering problem, a random forest is a strong baseline. This is from our experience. Okay, so if you don't know which machine learning algorithm to use, you should always try random forest first. Okay, this gives you a very good baseline. Okay, so I think it's very simple to now. I think it's very simple to train a random forest. Basically, you just define how many decision tree you want to train, and then for each of decision tree, you do a bootstrapped, and then you just randomly use some feature, and they will train the decision tree, and you train a lot of decision tree. Later, you just aggregate. Okay, so this is bagging plus feature randomization gives you the random forest. Okay, so that's the idea of bagging. And then we talk about the idea of boosting. The boosting is actually also very interesting. So basically, the boosting says that so it's also talking about the data, but in the boosting, it tries to reweight the data. So basically, it always puts more weight to the data that is difficult to be correct in the previous round. Okay, so for example, you have take a test, you take a test, and then you got something wrong, and then you will tell the second people that this question are difficult. Okay, so maybe I give you an example. So the boosting basically says, I skip the detail, so maybe I just show you the example first. Okay, the boosting basically says that here you can see that you have the data like this, and the first classifier gives you this classification. Okay, and this classification basically you got these 3 data wrong. Okay, and then next round I train the second classifier. And that when I train the second classifier, I highlight these 3 data. Highlight means that for example, I can repeat the data. I insert multiple data to the 3. And then the second learner will learn on this data set. And then the second learner may get something other thing wrong. So you can see this 3 becomes wrong. And then the third learner will have this 3 being emphasized. So this is called boosting. So boosting and bagging are different, completely different, right? Bagging is basically you can train a lot of methods in parallel, but this one is one by one. You train the first one, you get some hint. Then you train the second one, you get some hint. You train the third one. Okay, you keep doing, you keep training. So by doing this, you can see that each of the learner actually they have some strengths. For example, this learner is particularly good at this data. This learner is particularly good at this data. Okay, so each of the learner has some specialty. Okay, then you aggregate the information, you finally get the results. So this algorithm is called ADA boosting. Have you heard about this? Okay, so boost. I think I definitely heard about there's a package called XG boosting. XG boost. So this is a very famous machine learning package. XG boosting. Okay, so as long as you see some methodology that is called some boosting, basically they are using the similar idea. Okay, they are ADA boosting, gradient boosting, XG boosting. So there's a lot. Okay, so there are some modification, but the key idea is here. The key idea is basically if you got wrong, I will emphasize in next round. Okay. Maybe I skip the methodological discussion. So maybe I just talk about this page. So here you can see that the algorithm for ADA boost is like this. So basically you have the weight for each of the data, and at the very beginning is equal 1/n. And every epoch, you train a learner HT, okay? And you train the learner and then you compute the weighted error. And based on this weighted error, you can compute the importance, you can recompute the importance of each data point. Okay, and using this recomputed data point, you train a next learner. And eventually, what you are going to do, you just do a aggregate. You aggregate based on this alpha. Alpha is some importance. Okay, the importance is based on your error rate. Okay, if your performance is good, then I trust more on you, something like that. Okay, so boosting and bagging makes all those classic machine learning methods comparable to deep learning. Otherwise, they are not comparable. Deep learning is so powerful. Okay, so boosting and bagging gives, at least they are on the same level 5 years ago or 10 years ago. Okay, now even they are doing boosting or it's still not comparable to large models. Okay, but I think it's very good to know because it's very interesting to have this. You can see that this idea is actually very smart. That they're trying to develop those kind of methodology for machine learning, and even till now, I think even the XG boosting and random forest are widely used. Okay, so so for example, the support vector machine logic, those things usually you won't use in your practice because it's not very powerful. But the random forest and actually ADA boosting is good. Most of, if your problem is not that difficult, those methodology is actually pretty sufficient. Okay. Okay, so that finished the unsupervised learning part. As I also put some analysis for the why the setting of those. So you can see there are some complicated equation for this and for this. So there are some analysis why this work. Okay, so I just skip that part. Okay, so that's it for today. So I just later, so one thing I just want to mention. So we go back to the, we go to remember the package that I mentioned. So XGBoosting is a very famous package. Later, if you really want to do something, this is also one thing you can try. Okay, this one, XGBoosting. Okay, so basically, if you don't want to choose an algorithm, this is usually a good one. Okay. So most of the algorithm I talk about is here in scikit-learn. I think I mentioned this. Okay. So I think now you have the capability to read all those documents in this web page. Okay. Say for example, classification. We talk about. I give you a very brief discussion on linear regression. So so basically, there's no linear regression, but it's linear models. And in the linear model, we have least square. Okay, so if you are using 2-norm, then it's least square. So it's ordinary least square. We call it OLS. And if you have some regularization, then you have ridge and lasso. Okay, there are some more advanced called multitask lasso and elastic net. So it's just a modification of lasso. And LAR is also lasso. Okay, so these are all lasso. Okay, so OMP I haven't talked about. If you're interested, you can check. And Bayesian regression I haven't talked about. And logistic regression I think I talked about. Generalized linear model I think Professor Zhang talked about that, on this. It's basically linear model with some random error. Okay, and the gradient descent you can check. And quantile regression, I haven't talked about, but it's actually pretty useful in engineering. Quantile regression is talking about giving you a prediction with interval. Okay, it's not just one prediction, it's an interval. For example, I predict tomorrow's temperature is 20 to 23, something like this. This is called quantile regression. Okay, so you can see that I finished all the linear model parts. And I just mentioned that I didn't talk about anything related to kernel. Okay, kernel. And SVM, I haven't talked about that. If you're interested, you should read. And so SGD, so gradient descent, I talk a little bit. And KNN, I think I finished this part. And Gaussian process, this one is difficult, so I skip that part. And naive Bayes, this one is also quite, no one uses it now, so we don't talk about that. And this one, decision tree, you already know. So example, you can see that boosting, random forest bagging, voting, stacking. So here is about the example. Okay, and feature selections, unsupervised, those are more advanced topic. So tomorrow, sorry, next week we'll mainly talk about neural network. Okay, so that's the classification, and the regression I think is the same. Okay, so that's supervised learning and clustering. There are a bunch of algorithms. Okay, so clustering method, there are so many. Okay, you can see there are so many. But I only talk about k-means and GMM. Where is GMM? Gaussian mixture. Okay, so there are a lot of others. So if you want to know more, I would suggest that you learn this one, dbScan. This one is commonly used. Okay, a very good feature for dbScan is that you don't need to give k. Okay, dbScan will directly decide what is k. Okay, and also there's a very good feature for dbScan is that it allows outliers. Okay, dbScan is very commonly used in bioinformatics, I think. Okay, so if you're interested, try to read this one. Okay, so you can see that after the clustering, the dbScan can have 3 clusters with something that they believe those data are not belonging to any cluster. Okay, so this is a key feature for dbScan. Okay, and so that's clustering. Okay, dimension reduction I haven't mentioned. So model selection, I think I also talk about the cross validation, hyperparameter tuning, and those things. Okay, so you should be able to read this part. And pre-processing, this are very practical, just how to process the data. So I didn't mention this part. Okay, so you can see that this whole website, you should understand most of them. Okay, if you really want to implement some methodology that I mentioned, you just try to use a function here. Okay, don't write by yourself. Okay, because most of the time what you write is definitely not the state of the art. They are doing there's a lot of parallel computing, a lot of implementation details I haven't mentioned. Okay, so I think this website gives you a full picture of what is classic machine learning. Okay, so when we talk about classic machine learning, then there's a not classic machine learning. Basically, it's deep learning. Okay, so if you are writing if you want to develop some deep learning method, so you shouldn't use this one. Okay, this one has nothing to do with deep learning. Deep learning has its own package that you should learn. Okay, so I think next week I will try to give you an overview of deep learning. Okay. So recent years, you'll see most of the papers are by deep learning. So it's actually a super large community compared to this one. Okay, so what I can do, just give you a very brief overview. Okay, so okay, so that's it for today. So the homework is released. So please remember to submit on time. So it's online submission. You just write down or type in or you do anything, and you scan it and upload to the Blackboard. Okay. Okay, so that's it for today. If I have any question, let me know. Okay. Okay, thank you.